Hello everyone, my name is Ali Sabe and I'm a PhD student at the University of South Carolina. Today I'll be presenting our paper titled P4DDPI Securing P4-Programmable Data Plane Networks via DNS Deep Packet Inspection. So the agenda for today is introducing the domain name system and the attacks on it, followed by current mitigation strategies, and then background on programmable switches, followed by our proposed approach, implementation and evaluation, and then finalize with discussion, conclusion, and feature work. So to begin with, the domain name system is a hierarchical distributed database that was initially implemented to map human-readable domain names to machine-readable IP addresses. So, for example, you would query on the google.com, and then you will get IP address, for example, 8.8.8. Later, the domain name system became an essential part of the internet that can provide services such as post and middle server aliasing, load distribution, and others. On the right-hand side here, we have the high-level mechanism of what happens when you query a certain domain, and basically it will go to the DNS resolver, and then it will go either recursively or iteratively over the root server, top-level domain, Yahoo, all the way back to the host itself to get the IP address, and then it can query the server itself. That's on a high level brief. Since its conception, the attacks on the domain name system grew widely and wreaked havoc in numerous domains. So for instance, the Mirai botnet was able to launch an attack that reached basically hundreds of gigabits per second, and their main attack vector was the domain name system. And essentially, this security gap can be attributed to the nature of the DNS and handling records transparently, which means that the domain name system does not attempt to interpret or understand the records it's serving. And this is basically attributed how it was designed, because it want to be as much scalable and as possible, and want to accommodate feature extensions as well. So that's why it was designed like that in the first half. So what are the existing architectures? Existing architectures addressing the main DNS attacks. So first we have the traditional enterprise networks, where you can basically use a number of components such as intrusion detection, intrusion prevention, access control list to protect against security threats. However, distributing these security functionalities among multiple components would create problems where basically managing these components would become really tedious, and let's say multiple components, different vendors, different configuration, so become really hard. On the other side, you can use one component such as a full-fledged firewall. However, when you restrict it to a certain component, this will degrade the throughput as much as you increase the security functionalities. Current contemporary architectures also offer solutions as the software-defined networking / OpenFlow, in which basically you can implement the security functionalities at the control plane. So packets will pass through this control plane, and you can also install rules according to the OpenFlow specification. However, the restrictions of the SDN paradigms or the limitation can be attributed to the if the packets go to the control plane, which run on a general purpose CPU, then basically this will cause a significantly lower speed. And also the rules in the data plane are restricted to the OpenFlow protocol. So moving from here, to advance the data plane or the OpenFlow, there's a new programming language called the P4 language that basically allows you to program the data plane. So it's basically overcomes the limitations of the OpenFlow, which we'll discuss here. So what are the P4 overview on the P4 switches? As mentioned, they overcome the limitations of the OpenFlow, in which they allow the programmer to program the data plane, so it's no longer restricted to a certain vendor. It's no longer restricted to the OpenFlow specification. The P4 program is a choice of the programmer or the network operator. And this, interestingly, this doesn't come on the expense of the throughput. So you'll have a terabits per second throughput while you're having your customized protocol. And also, once you compile the P4 program, you don't have to worry about the throughput if it's gonna degrade or not, because once it runs, it will compile on the chip. It will run on the chip assignment. So our proposed system is basically to leverage this technology, the P4 technology, in order to perform DNS inspection in the data plane without using a general purpose CPU or a firewall. And so we want to do a deep packet inspection so that the data plane now is able to parse these DNS packets and apply some security rules, access controls, filtering, and so on. So our main topology here is that, or assumption is that our P4 switch lies between the domain name system resolver and the network host. So all the DNS traffic passes through the P4 switch. The P4 switch will apply deep packet inspection on the packets in order to match and perform the security functionalities, which can be basically DNS filtering, URL filtering, monitoring, and so on. So this is our architecture, and as mentioned before, P4 is really flexible and it really allows you to customize your P4 program without sacrificing the throughput. However, it also has its own limitations. So for instance, you will have the limitations of the P4 include the hardware limitation, basically the memory inside the P4 switch, as well as the P4 language itself. So, for example, in P4 language, you can't explicitly write loops. You can deeply parse the packet. You can apply too many batch actions. So this is all depends on the number of stages in the architecture of the P4 switch. So in order to as you know here, the domain name system would have a variable name. So for example, querying Google is different than YouTube and so on. In order to do that, what we did in the data plane is that we kind of emulated loops using a technique called packet recirculation. So the DNS reply or the DNS query comes to the P4 switch. The P4 switch will parse a limited number of labels, not all the labels at once. And then once, if it needs more deep packet, if it needs more parsing, then the packet will recirculate the DNS then in order to perform more deep packet inspection. Once the DNS is basically parsed, the switch can store the IP address of the server, DNS server, client, can perform some traffic blocking, monitoring, and so on. And this is our architecture and the algorithm that we followed. As mentioned earlier, we first per every packet recirculation, we only parse 4 labels. We hash them, so we don't match on the label itself, but rather we match on the hash to minimize the to overcome some hardware limitations. And then we keep recirculating and sending the concatenation of the hashes until the whole domain name system is parsed. So our implementation and evaluation setup is as follows. We have two hosts and the pfsense firewall. And essentially we connect all through 40 gigabits link. The host, they generate network traffic through ipperf as well as DNS traffic using DNS traffic generator. And all the hosts and pfSense run on a dedicated server. We'll also have a P4 switch edge core wedge, which can serve up to 3.2 terabits per second. And we will basically sending traffic between the hosts as well that parse through the P4 switch and pfSense. So the first metric that we wanted to evaluate is we wanted to compare the throughput between P4DDPI and pfSense, which is a general purpose CPU firewall. So what we did is that from host H1, we started sending normal background traffic using PyPerf. And at t equal 120 seconds, we started sending DNS queries. And every 1 minute, we increased the DNS query rate starting from 1 megabits per second all the way up to the 200 megabits per second. As we can see here, pfSense, the throughput of pfSense started decreasing when the DNS rate was like below 6 megabits per second, which is considered normal according to Google. And that means like just enabling DNS inspection in pfSense would really degrade the throughput. And on the other hand, in P4DDPI, there's no performance penalty was observed. Another metric that we were interested also in measuring is the delay, of which how long the DNS packet spends in the P4 switch or the pfSense firewall. And so we use, in order to measure accurately the timestamps, we use also a P4 switch to tag on the egress packet and just measure how long the packet stays. As you see here on the right hand side, the graph, the delay in pfSense can go to milliseconds. However, on the P4 switch, literally parsing the DNS would takes hundreds of nanoseconds. So it's like it's very, very fast. We were also interested in measuring the packet loss. So how much packets are lost in pfSense and P4DDPI, but we followed the same setup and topology as in the throughput, so sending background traffic and DNS traffic. And as we mentioned here, also we measured the packet loss and the P4 switch itself. What we realized here is that the pfSense has a loss rate between 0.84 and 1.1, whereas in P4 there's literally no packet loss, no packet loss at all. And for the DNS packets, we noticed that increasing the rates in pfSense would significantly drop DNS query. This is, by the way, the loss of the normal background traffic and not the DNS query. We also evaluated the CPU usage of pfSense, and as we can see here, it was varying DNS rates. As we can see here, the CPU utilization increases exponentially to reach 100% at 50 megabits per second. However, because P4DDPI doesn't use general purpose CPU, but it uses the ASIC, so it can process terabits per second without any performance. We also compared P4DDPI with Metaphor, which is also a similar framework that inspects DNS packets using the P4 language. However, they only parse 4 labels with up to 15 characters. So they don't do the packet inspection as we do. And this is essential for security functionalities, what we do. And we use the data set in order to see how much traffic is missed in our approach and how much traffic is missed in their approach. It is reported here 4% of malicious traffic in this data set is only missed in our approach, whereas 17% is missed in their approach. And we'll see the reason for the 4% there in a second. P4DDPI, these are the resources that are occupied in the switch, where we notice here there's like minimal resources used. And this allows us basically to have more functionalities in the P4 switch. As a discussion, P4DDPI can be mostly realized in high-speed networks where security and performance are both required. Uh, However, like the P4 switch is not intended to fully replace firewalls because there are a lot of hardware and software limitations. So in our approach, per label, we are only restricted to 19 characters only, and that's due to the parsing and match action. And we can only store 200,000 entries in the domain. So if you want to filter, perform domain name filtering, you can only store in the data plane up to 200,000. More than that, you will need the control plane to store these rules. Also, DNS can't handle the encrypted traffic, but this is not restricted to the P4 language. It's basically applies also to general purpose CPU. As a conclusion, we presented P4DDPI, which performs the packet inspection using P4 by leveraging P4 recirculation, packet recirculation techniques to parse any number of labels in the domain. We evaluated P4DDPI against general purpose CPU, where we realized the gain that we can get in throughput, delay, packet loss against CPU firewalls. And we also evaluated against the P4-based approaches, where we see that our approach is capable of parsing more labels. As an acknowledgement, we would like to acknowledge the NSF for funding this project, and thank you very much.